Welcome back, friends, to another session of fluid mechanics and rate processes. In the last session, we looked at how a viscous flow at large Reynolds number could actually be broken up into two parts: a boundary layer which is close to the surface of the body, where all the viscous effects are accounted for, and then away from the boundary layer, we could actually call that as an outer flow. And the idea was that here the viscous forces are not important at all and viscous effects can be neglected. So, that is how we can simplify a viscous flow. So, one can now look at two aspects of these real flows. One, a boundary layer flow close to the body, and then an inviscid flow away from the body. So, we are going to spend the remaining part of the semester in understanding these concepts. So, today I want to talk about the inviscid part of the flow. These flows essentially imply that the viscosity is 0. So, mu is 0, that is what inviscid flow is, and these are usually governed by Euler equations. Just to refresh your memory, these are again two sets of equations: the mass balance, wherein divergence of velocity field is 0, and then we had the momentum equation, where we have the unsteady term, then the convective acceleration, and then the pressure gradient, and this now is equal to the body force, because we do not have to worry about the viscous term. And we made a comment that even though these equations are one order lower, so these are first order in V, unlike the viscous flow equations. So, maybe I should write here, unlike viscous equations, that are second order in velocity. Okay. So, this is good news, but the problem is that they are still nonlinear. So, we still have to deal with this term, which causes some difficulty in getting solutions. And a fallout of the nonlinearity is that we cannot superpose flows. I am going to say a little bit more about this when we go to flows where one can superpose and where one has linear equations. So, we will hold on the discussion till that point. So, what can we do further? It turns out, and we are going to see, that if the flow is irrotational, and that is an if, then further simplification is possible. So, now obviously we would like to understand when are the flows irrotational. We have talked a little bit about it, so we are going to review that. And what if the flows are irrotational? Then how do we further simplify these equations? I can already tell you the answer, so that you can comprehend what we are going to discuss. It turns out, if you have an irrotational flow, then the velocity field can be expressed as the gradient of a scalar, which we call as a potential. And then beautifully what happens, that this equation, which seems to have 4 unknowns right now, 3 velocities and pressure, and they are coupled. If we had an inviscid flow which is additionally irrotational and a couple of other conditions, then I could decouple velocity and pressure. So, I would get an equation simply in terms of the potential, okay? and that would be a linear equation, and I can use that to get the velocity field and then use the Bernoulli's equation to get the pressure field. Okay, so the simplification becomes enormous. Instead of having 4 coupled unknowns, I am reduced to just one single scalar, the velocity potential. Okay? And then I can also superpose flows in the sense that if I have building blocks of certain flows, I can construct more complex flows by combining them. So, all this we are going to see. So, the next concept that we want to talk about is irrotational flows. We have already discussed this when we did the flow kinematics, but let me recollect your thoughts. So, kindly recall that if I talk about the gradient of velocity, okay, so I have a velocity field and gradient tells me how it is varying in different directions. This we said we could decompose into a symmetric part. So, there was a gradient of V plus a gradient of V transpose. So, this is the symmetric part, and then there is another part which is the skew symmetric part, which is gradient of V minus gradient of V transpose. So, this is the skew symmetric part, right. And what we were able to argue and show is that the symmetric part is actually the one which relates to the strain rate, and for a Newtonian fluid we were able to relate the strain rate tensor to the stress tensor. Okay. So, if you recall, we said that for a Newtonian fluid the stress basically tau was something like minus P. So, that is the hydrostatic pressure, and then mu times the strain rate, 2 mu, in fact there was a factor of 2, twice of mu times the coefficient of viscosity times the strain rate. So, this includes the, what does the strain rate include? From the kinematics we recall this includes the dilatation, right. It also includes the shear. So, all these are rate, and of course, the extension. This was the symmetric part. The skew symmetric part was related to omega, which essentially is the angular velocity of a fluid element. So, we were able to work out that the skew symmetric part, by definition the diagonal elements are 0 and the off diagonal terms are non-zero, but then they are kind of related to each other through a negative sign. Okay. So, there are only 3 non-zero or 3 unique components that we can find in this matrix, and they were related to the angular velocity. And in fact, we were able to show that omega is actually in fact half of omega gives rise to the rotation rate, and this omega was curl of velocity. Okay. So, let me now recap the whole thing for you. I have a velocity field, and from kinematics I have been able to break it into 2 parts, a symmetric and a skew symmetric. The symmetric part gives me what would be useful in a constitutive model, the strain rate tensor, and the skew symmetric part tells me how these elements are spinning about their own axis, and the rate of rotation is omega, and this omega is also related to the curl of velocity, which we are denoting by the small omega, and there is a relationship between the angular speed and the curl of velocity. This we already know. We had also discussed in fair detail what is meant by this rotation rate and what would happen if this is 0 everywhere. So, we had proposed that if omega is 0 everywhere, then we have something called an irrotational flow. So, there are two ways of checking irrotationality. One is you could go and check the angular spin rate of each element about its own axis, or you could simply look at the vorticity, the curl of the velocity. If the curl of velocity is 0 everywhere in the flow, then you have a irrotational flow. So, this also implies curl of velocity is 0 everywhere. Let me just refresh your memory with some of the examples that we had talked about. So, in 2D, if you remember, my omega is simply omega z times k. Okay? So, if I have a two-dimensional plane, then the vorticity vector is actually can be represented by simply a scalar, and if this is my plane, then it points outward in the k direction. How is that given? So, omega z, if you remember, was actually del V y by del x minus del V x by del y. Okay. So, we also looked at some examples that what does omega z equal to 0 imply. Okay. And the example that we gave was that if I have circular streamlines, then it does not necessarily mean that omega z is non-zero. Okay. So, so let me then just remind you that I will take two examples. So, first is, does streamlines being circular imply omega z is not equal to 0? That is one question that we addressed. And the second question that we want to ask is that can straight streamlines lead to omega z equal to 0, right. So, this would help us understand what is rotationality or irrotationality. So, let us first take example 1. Okay. So, I want to take circular streamlines and then try to argue that under what conditions you would get a rotational versus irrotational flow. So, I will draw two sets of streamlines. So, these are my streamlines, okay, kind of circular, and let us say this is the direction of the flow. For simplicity, let me talk about a steady flow. Okay, so, it does not change with time. Simply by drawing these streamlines, can I conclude that this flow is rotational or irrotational? The answer is no, okay, and as I will illustrate. So, it really depends on the fluid element. So, let me give an example of a free vortex versus a forced vortex. In a forced vortex, I am going to have a velocity field where Vr is 0 and V theta is k r. What that means is that there is no radial speed, so there is only a tangential speed, and it varies linearly with increasing r. Okay, so it is almost like a rigid body motion. And here what is happening is that if I draw fluid elements, which you can, at these different locations, then what I need to ask myself is that when this fluid element moves as a rigid body, does it rotate about its axis? And in fact, you can check from this velocity field that actually, because it is a rigid body motion, so the element goes like this. Okay. So, it actually, when it does one revolution around the central axis, it also does a rotation about its own axis. So, let me just indicate that with a arrow. So, let me say this is the orientation of the element at this location, and then what I would find is that this element actually goes like this, then it actually goes like this, and further it goes like this. Okay. So, again, to show you, the element would be doing this. Okay. So, it is actually spinning about its axis as it rotates. This flow would be a rotational flow. It is a vortex because my fluid elements are doing some kind of a revolution about a central axis. Okay. So, that is what a vortex is. You would have some kind of closed streamlines. They need not be circular, they could be elliptic, but the fluid element makes some rotation about a central axis. How about a free vortex? For a free vortex, an example is the radial speed is 0 and v theta would be something like k by r. So, I am not arguing this for you how the fluid elements would behave from this speed. You can check that by working it out, but the effect of this velocity field would be the following, that if I consider a fluid element as it goes around, you would see that with this velocity field it does this, in the sense that the fluid element does a revolution about the central axis, but it does not spin about its own axis. So, just for completeness, let me draw the arrowheads here. So, what you would then find out is that an element which is oriented like this would actually keep getting oriented in the same manner at all locations. And this would be an example of irrotational flow. Okay. So, that answers the first question. So, remember, we had asked ourselves two questions. The first question is, if the streamlines are circular, does it automatically imply that my flow is rotational? And I have already given you a counter example that no, it does not. Both are circular streamlines. The force vortex is rotational and the free vortex is irrotational. Okay. And as I told you earlier in the session, that if you had an inviscid flow with an irrotationality condition, it would actually help us in the analysis. Okay. Now, we come to the second question. If I have straight streamlines, am I guaranteed that omega z is 0? That means it is a irrotational flow. So, let us try to answer that. Okay, so now we are going to ask ourselves the second question, what if streamlines are straight. And here I would like to give you the example of the plane Couette flow. This was discussed earlier, the flow between parallel plates. So let me draw the parallel plates for you. So the pressure gradient is 0. So dP dx is 0. This was the x axis at the center line, and there is a y axis here. So this is flow between infinite plates. The upper plate is moving to the right with a speed u, and the lower plate is stationary. And we had worked out the velocity profile. This was the velocity profile. Okay. So what we had found is that Vx was given by this expression u by 2 1 plus y by b, if b is, so this is y equal to minus b, this is y equal to plus b. So 2b is the distance between the two plates, you get a linear velocity profile, and of course Vy is 0. So therefore if you draw the streamlines are straight lines, simply because Vy is 0, so you would just get streamlines. And that's the question we are asking. Does this make the flow irrotational just because there are straight streamlines? So one can now calculate what is omega z for this flow, and that's of course given by del Vy by del x minus del Vx by del y. This term goes away, there is no Vy, and this turns out to be minus u over 2b. So if I look at the rotation of the fluid elements, that would be half of omega z, and that would be minus u over 4b. So the expression tells me that the rotation rate is negative, which means it is clockwise. Okay, counterclockwise is positive. So now let us on this diagram try to understand what happens to fluid elements. So if I take a fluid element at a certain time, so let us say I take this fluid element and I ask myself what happens to it after time delta t. So the fluid element convects, and these two edges, they convect with the same speed, but the upper two edges, they convect with a slightly larger speed. So at a later time, this element would look something like this. And if I look after a little bit more time, then I would find that I get this, and this deforms even more. And indeed, this fluid element seems to be rotating. So if you kindly recall that omega z, which is the rotation of, or the rotation rate of the fluid element, is actually the average rotation rate of the two perpendicular edges. So in this example, this very special example, you will find that the lower edge does not rotate, simply because of the way I have chosen the element. Okay, it is aligned with the x axis. So this edge just stays aligned with the x axis. But the edge which was initially aligned with the y axis, that rotates, and therefore the average rotation of this element is in the clockwise direction, and in terms of the quantitative analysis, this is what it is. So, is the flow rotational or irrotational? The answer is, of course, this is a rotational flow. Right? So, therefore, rotationality has not much to do with the direction of streamlines. I have shown you an example that I could have straight streamlines and still have a rotational flow, and I could have circular streamlines and still have an irrotational flow. Okay? You can ask similar questions, that what happens inside a boundary layer. So, let us try to argue inside a boundary layer. If you recall from the previous session, we had taken flow past an airfoil. This was the free stream flow, and then we argued that we could decompose this flow into two parts. This here is the inner solution, and the outer one is outside this layer. Here the flow is highly viscous, and here the flow is inviscid. Okay? If I look at a typical velocity profile, let us say at this point, the profile would look something like this. And as you can guess from the example of the plane Couette flow, inside the boundary layer I definitely have a rotational flow. Okay. So, this inside the viscous boundary layer I would have a rotational flow. However, the outer flow being inviscid, it could be a rotational flow or it could be an irrotational flow, and the argument we are making is, if this flow is irrotational in addition to being inviscid, then we should be able to simplify our analysis. Okay, and that's the whole case that we are building. So, I hope now the analysis, the way we are going to do the analysis is going to be clear, that when we are interested in solving a viscous flow for, let us say, an airfoil at a large Reynolds number, then this region is extremely thin. We saw in one of the sessions, it could be simply of the order of a millimeter if the chord of the wing is about 5 meters. We saw that for the example of a flow over a wing of a Airbus A320. So, if we can show that the outer flow is inviscid, we will have a simpler analysis for that, and we are going to use the boundary layer for the inner solutions. Okay. So, one last thing before we move on with the analysis, and that is, can I say that all viscous flows are rotational? So, maybe I should put a question. Are all viscous flows rotational? And I can give you a counter example. What if I had a uniform flow? So, I could have a uniform viscous flow. Okay, so, there is a breeze and there are velocity vectors aligned to each other, and it is a uniform breeze everywhere, and there is no gradient in the flow. And you can then argue that there would be no rotation, because omega you can actually calculate would be 0. So, you could have a situation where the flow is viscous and it is irrotational, versus if I go inside the boundary layer, Again the viscous effects are very important, but this would be a rotational flow. So, one has to be very careful. On the other hand, I could have inviscid flows, and I could ask, are inviscid flows always irrotational? And we have just looked at some examples. So, I gave you the example of a forced vortex and a free vortex, and they both could be in the context of an inviscid flow. So, viscosity is 0. So, an inviscid flow, which is a free vortex flow, is an irrotational flow. On the other hand, an inviscid flow with a forced vortex is a rotational flow. Okay, so, I hope the concept of rotationality is now clear to you. We are now going to introduce another concept, which is circulation. So, by definition, circulation is denoted by gamma, and we are going to define this as a line integral over a curve C v dot ds. So, the idea is we can take any curve C, and there is a velocity field in this plane. So, this could be a 3-dimensional velocity field, and the curve could also be a 3-dimensional curve. And if I take a small element of it, an infinitesimal element, let me call it as ds, and of course, the velocity vector could be aligned at another angle. So, if I go around this curve and do this calculation, that is what is called circulation. By Stokes' theorem, I could relate this integral, the line integral on a curve, to an area integral, and I could write gamma as simply integral over an area A, and this would be the curl of the velocity dot dA. Okay. So, let me show you with a diagram what this curve is. So, if I draw the curve, so this was my curve C, and now I am enclosing it with an area. Okay, so, this is some kind of a surface, and this, so you can imagine that this surface is capping this area, and what is being said is that I can take this little curved element here, which is dA, and it has a unit normal vector. So, whether I do an integral on this curve C or I do an area integral over this cap. So, I could think of a hat. Okay. So, I could place a hat on this curve and do the area integral on the periphery of that hat. Okay. So, that is what the Stokes theorem tells me. So, the surface A of the curl of velocity on this area A, which is actually the open surface that encloses C. Okay. All right. So, we have defined this circulation, and you have two ways of calculating it, either directly through the velocity field, or you can relate it to the curl, which of course we are denoting with vorticity, and these two are identical in 2 dimensions. If I take a very special case, then I could do the following. gamma is over the curve C V dot ds, and this is actually equal to integral over the area A, which is omega z and times dA. Let me show this pictorially. So, if I took this curve C and I broke it into these different elements. So, this entire area is A, and suppose I call each one of these as dA, then either I could calculate gamma by doing a velocity integral over this curve C, or I could calculate the vorticity everywhere in this area, and then I would have these vorticity, and I just take the average of this, not the average, sorry, the summation of it, omega z dA. So, I just take the summation of all the vorticity enclosed by this curve, and that is your gamma. Okay, so, that is in 2 dimensions. So, in some sense what we are saying is that circulation is actually the sum of all the vorticity in the area enclosed by closed curve C. Okay. This should now help us interpret irrotational flows. So, if I have an irrotational flow, that means omega is 0 everywhere, right. So, this actually implies that my gamma is 0. So, if gamma is 0, then I have an irrotational flow. So, I have 2 ways of checking irrotationality. Either I could check omega is 0 everywhere, or I can simply check if gamma is 0 through the line integral. They are synonymous statements. And this brings us to an important theorem, which is the Kelvin's circulation theorem. So, Lord Kelvin he derived many important results, and one of them is particularly useful for us here, which says that in an inviscid flow with conservative body forces, the circulation around a closed curve moving with the fluid remains constant with time. So, what the Kelvin's theorem tells us is that if I have a flow and I decide on making a certain curve C, and that curve is going to obviously enclose certain fluid elements. But now I move this curve in time so that it encloses the same set of fluid elements at all times. So, essentially the curve convex with the flow, okay, it encloses exactly the same elements at all times. Then he says that the material rate of change is 0, which means d gamma dt is 0. So, this is Kelvin's theorem. It is a very important result. Let us look at the operating conditions. If I have an inviscid flow, and of course I am only using gravity, only accounting for gravity as the body force, which is a conservative force. So, this holds for inviscid flows. In an inviscid flow, if my flow is initially irrotational, it will remain irrotational at all times. If it has a certain gamma to begin with at t equal to 0, it will retain the same gamma at all times. So, it is a very important result. It is somehow related to the conservation of angular momentum. Okay. So, so the fallout of this is that, so maybe I should summarize that here. So, this implies that flows, of course we are talking about inviscid flows. So, maybe I should clarify that inviscid flows that are irrotational at t equal to 0 remain irrotational at all t. Okay. So, let us understand what we have said so far. So, we started off with a flow at large Reynolds number and we broke it into an inner flow and an outer flow. The outer flows we have assumed it is to be inviscid, okay, viscous effects are negligible. So, they are governed by the Euler equations, but Euler equations are still complicated for us. Okay. So, we are asking ourselves, suppose the flow is irrotational, then can we have a simpler analysis? Okay. But for the flow to be irrotational, what are the conditions we should satisfy? And we have seen we should have, of course, omega is 0 at all locations, and we also saw it is synonymous with gamma equal to 0, the circulation being 0. And the Kelvin's theorem tells us that it is enough to have irrotational at one time instant, and you should be then able to generalize that it would be irrotational forever. Okay. So, we will now talk about a concept which is the velocity potential. So, let us consider a curve. So, this is the curve C, and let us say there are these points on it A, B, C and D. Now, I have an irrotational flow and therefore, I can say the circulation calculated on this curve C is 0. So, gamma is defined as the circulation on this curve C, the closed curve, V dot ds, this is 0. Now, the curve C, as you can see, is in this manner A, B, C, D, A. So, I just have to go around it. What I will do is, I will decompose this integral into two parts, which is from A through C. So, I will write this as, so now it is not a closed curve. So, it is an integral A, B, C V dot ds and then integral over C d A. v dot, this is 0. Essentially, the sum of these two integrals is 0, or in other words, this integral is negative of this integral. So, I will rewrite it as integral over a b c v dot ds. This is integral over v dot ds, and instead of putting a negative sign here, I am going to reverse the direction. So, instead of going from c d a, I will now go a d c. Okay. So, what I am now saying is that because the circulation is 0, so I am reinterpreting this whole thing as, let me fix any 2 points A and C, and I can take any arbitrary curve that goes through these 2 points A and C. And what I am now able to show you is that this v dot ds is independent of the curve that I choose. Okay. So, what this result shows is that integral v dot ds between A and C is path independent. And the argument is because C is arbitrary. So, maybe I just write it down, C is arbitrary. So, now this leads to certain mathematical deductions, which means that v dot ds, the integral between A to C, I should be able to write it, if it is path independent, as some value that depends on C and some value that depends on A. Okay, because this is path independent, it only depends on the states A and C. So, therefore, I should be able to say this quantity is the difference between the two states. And this implies that this v dot ds is a total differential. Okay, so, this therefore implies that v dot ds is a total differential, and this must be d phi. And this would imply that v is actually gradient of phi. Okay. So, what we have shown is that if I have an irrotational flow, and the irrotationality, let me recall for you, was that each element is not spinning about its individual axis. Okay, the rate of rotation is 0, and that we were able to relate to circulation. So, for circulation being 0, we are now able to show that this implies velocity can be expressed as a gradient of a scalar function. This phi is known as velocity potential. Okay, simply because v is the gradient of this function phi, and flows which have a potential, which means the velocity potential, are called potential flows. So, if somebody asks you what is a potential flow, essentially a flow that is inviscid, it is irrotational, is known as a potential flow. Okay. All right. The fallout of this is that, as I said earlier, that instead of v being a vector with 3 unknowns, you have reduced the problem to a single unknown, which is a scalar. So, we will continue on this in the next session, and before we close today, I just want to remind you of another concept, which is the stream function. This would also be very useful. So, please recall a streamline. We had talked about a streamline a few sessions earlier, and we said that along a streamline, if I take any point and draw a tangent on it, then the tangent points in the direction of velocity vector. Okay, so if I draw a streamline, then tangent at every point gives me the direction of the velocity. So, this would be a streamline, this would be another streamline, and this could be another streamline. So, these are all streamlines, and as a corollary, flow cannot cross streamlines. So, if I take two sets of streamlines, they form a stream tube. If I took a set of streamlines and formed a surface in 3 dimension, then I could get a stream surface, okay? And if it is closed, it is a stream tube, but it need not be closed and it would still form a stream surface. Okay. Now, the way we defined a streamline, we had done this in earlier session. If ds is a vector along the streamline and v is the velocity vector, then along the streamline ds cross v is necessarily 0, and therefore, we were able to say that if I do I j k dx dy dz, this is vx, vy, vz, this is 0, and this would give me the equation for a streamline. So, the equation of a streamline would be that vz dy minus vy dz is 0. For the j equation, I get vz dx minus vx dz is 0, and for the k direction, I get vy dx minus vx dy is 0. So, these 3 equations represent a streamline. If I restrict myself to 2 dimensions, then this is the relevant equation, and it tells us that dy by dx, that means the slope of a streamline is essentially given as vy by vx. Okay. So, this can be used to find an equation of a streamline. We can actually define a stream function. Such that, so this stream function is psi and it is x, y and t in 2D, in 2 dimensions. And here I could say that psi equal to c is a streamline. Okay. And if I just do different streamlines, this could be psi equal to C1, psi equal to C2, psi equal to C3. So, these are 3 different streamlines that I have drawn, and one can show that the difference between these constants would give me the flow rate. So, if I did C2 minus C1, that would give me the flow rate between 2 streamlines. Okay. So, in 2D one can show that I can relate Vx and Vy to the stream function, and I am just giving you the definition. So, Vx is given as del psi by del y, and Vy is del psi by del x. Okay. In 3D, psi is no longer a scalar, but a vector. Okay, so let me review what I have shown you. If you had an inviscid flow, then it is possible to further check if the flow is irrotational, and if it is inviscid and irrotational, you can define what is called the velocity potential. And velocity potential simply is a scalar, the gradient of which will give us the velocity field. Okay. But we can also talk about a stream function, and here we are saying that we have not invoked anything about rotationality. A stream function would exist for all kinds of flows. However, if we restrict ourselves to 2 dimensions, then we can define a stream function psi and get the velocity field Vx and Vy by taking simply the spatial derivatives of this stream function. So, now we have these 2 variables psi and phi, the stream function and the velocity potential, and we will go back to the Euler equations which actually govern the flow for an inviscid fluid, and see that if further our flow is irrotational, how do these concepts of stream function and the velocity potential simplify our governing equation. We will do that in the next section. Thank you very much.